Unit 9.7 is circles and lengths of segments. This time we're not going to be dealing with angle measures. We're going to be dealing with segment lengths. And this is all based on similar triangles. We could create all of that. We're just going to kind of look at the theorems here. When two chords intersect inside of a circle, then they are divided into two pieces such that piece times piece of the first chord equal piece times piece of the second chord. Okay? Now here's what it says if you say it fancy. If two chords intersect inside of a circle, then the product of the segments of one piece is equal to the product of the segments of the other. If two chords intersect inside of a circle, then the product of the segments of one chord is equal to the product of the segments of the other. Product means multiply. The segments are the pieces. So piece times piece of this one equal piece times piece of that one. The product of the segments of one chord is equal to the product of the segments of the other. Okay, so you can study that fine print. I'm just going to cut to the chase here. If two chords intersect inside of a circle, then the product of the segments of one chord, this chord has been busted into two pieces, A, B, and 3. So the product of the segments of this one, 3 times AB, is equal to the product of the segments of this one, 6 times 4. Piece times piece of this one equal piece times piece of that one. The product of the segments of this one is equal to the product of the segments of that one. Now, to simplify, we're going to go ahead and multiply there. So we have 3AB is equal to 24. Undo multiplication by division, and we get AB is equal to 8. If two chords intersect inside of a circle, they are divided such that piece times piece of the first is equal to piece times piece of the second. The fancy way to say that is the product of the segments of the first chord is equal to the product of the segments of the other. Okay? We have two chords intersecting inside of a circle again. That chord is divided into the pieces 5 and 6. This chord was divided into the pieces 10 and X. Piece times piece of the first chord is equal to piece times piece of the second chord. In other words, the product of the segments of the first chord is equal to the product of the segments of the other. We're going to undo whoops, we need to, got ahead of myself. We need to go ahead and do the multiplication first. We would have 30 is equal to 10x. Now we're going to undo multiplication by division, and we would get x is equal to 3. If two chords intersect inside of a circle, then they're divided such that piece times piece of the first is equal to piece times piece of the second, meaning that the product of the segments of the first chord is equal to the product of the segments of the other. Okay. Theorem 910. If two secants are drawn to a circle from a point outside, then the one whole secant times its outside piece will be equal to the other whole secant times its outside piece. The fancy way to say outside piece is the external segment. And so the way you say this fancy is, if two secants are drawn to a circle from a point outside of the circle, then the product of one secant and its external segment, the product of one secant and its external segment is equal to the product of the other secant and its external segment. Okay? If two secants are drawn to a circle from a point outside of a circle, then the product of one secant and its external segment is equal to the product of the other secant and its external segment. Again, what that means to us is that this whole secant times its outside piece is equal to this whole secant times its outside piece. Okay? And it says here, remember the quadratic formula. Standard form of a quadratic is ax squared plus bx plus c equals 0. And to find the values of x that would make y equal 0, you can use the quadratic formula. X is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. That's on page 221 of the Algebra 1 textbook, I believe. Page 221 of the Algebra 1 text to study the quadratic formula. It's there in chapter 7. Okay? So, let's just kind of clean house a little bit here. Just going to get right down to the math. I chopped off too much. Okay, we have two secants drawn to a circle from the point outside. So this whole secant, 16, times its external segment, DC, is equal to this whole secant, which is 8 plus 4, which is 12, times its external segment, 4. So one whole secant times its outside piece is equal to the other whole secant times its outside piece. We're going to multiply. We will have 16 DC is equal to 48. We're going to undo multiplication by division, and we will have DC is equal to 3. Okay? Let's look at the second example. We have two secants to a circle from a point outside. So this whole secant, 12, times its outside piece, 3, is equal to this whole secant. How would you get that? You'd have to add the pieces, 5 plus x, times its outside piece, x. So if two secants intersect a circle from a point outside, then one whole secant, 9 plus 3 is 12, times its outside piece, 3, is equal to the other whole secant, 5 plus x. 5 plus x. See that? 5 plus x. Times the outside piece, x, times x. times the sum or difference. You have to put that sum or difference in parentheses and distribute. That's rule page 37 of the Algebra 2 text. It's also distributive property law on page 171 of the Algebra 1 text. We said you can only distribute onto a one lesser operation. So over here we're going to do the multiplication. We're going to get a 36. We're going to distribute on the right. X times 5 is 5x. X times x is x squared. Now we have a quadratic. We learned about these in chapter 7 of Algebra 1. We know it's a quadratic because it has an x squared and an x. That's two different names, so you cannot solve using the order of operations. So what we're going to do is write it as a quadratic in standard form. Standard form of a quadratic is ax squared plus bx plus c equals 0. You find that in the Algebra 1 text on page 194. We're going to solve in a moment with the quadratic formula. The quadratic formula is on page 221 of the Algebra text, and it's in this lesson also. It says to find x, you would take the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. But before we can identify the a, b, and c, we must first write it in standard form. Standard form is set equal to 0. So we set it equal to 0. We're just going to stick it under there. We're going to put the x squared first, the 5x second, the negative 36 third equals 0. We've got the x squared stuff first, the x stuff second, the number third. It's set equal to 0, so that puts it in standard form. The a is the understood 1, coefficient of x squared. B is 5, and c is negative 36. We're going to plug those numbers into the quadratic formula and solve. So we're going to get x is equal to the opposite of b. B was a positive 5. The opposite of that is a negative 5, plus or minus the square root of what b is square minus 4 times the a of 1 times the c of negative 36 all over 2 times the a of 1. And then we're going to solve. We can do the 5 squared and all this multiplying and that multiplying at the same time. And don't forget, when you do all this multiplying over here, that we're going to call the sign of that 4 negative and the sign of that 36 negative. And so we're going to have x is equal to negative 5 plus or minus the square root of 5 squared is 25. 4 times 1 is 4 times 36. 4 times 36 is 144. When you multiply or divide with an even number of negatives, the answer is positive, so we put a plus right there. All over 2 times 1 is 2. Now we're going to combine like terms. And so we're going to have x is equal to the opposite of b, negative 5 plus or minus the square root of 25 plus 149 is 25 plus 144 is 169 over 2. Now we're going to take the square root of 169, which is either 13 or negative 13. Remember on page 26 of the Algebra 1 text, example 5, we said to get rid of the square, it's x squared equal 36. In x squared equal 36, the x is a 6 or a negative 6. To show your work algebraically or to solve algebraically, you undo the square with the square root, and you do plus or minus square root of 36, which is plus or minus 6. So when you take the square root, you do plus or minus square root of, which is going to give you two answers. So we're going to have x is equal to negative 5 plus or minus square root of 169, which is 13, all over 2. Now, at this point, we split it into two equations. This turns into 2. X is equal to negative 5 plus 13 over 2. And I'm going to have to erase some stuff here. I'm getting a little bit congested. So x is equal to negative 5 plus 13 over 2, or x is equal to negative 5 minus the 13 over 2. So here we would have x is equal to negative 5 plus 13 is 8 over 2, which is 4. Here x would be negative 5 minus 13 is negative 18 divided by 2, which would be negative 9. Now x is how long ij is, and it can't be negative, so we kick that out and accept the positive value. So x is equal to 4. So that one turned into a quadratic, and we had to use the quadratic formula to find the value of x. Any questions on that? So here's what we've learned so far. We said if two chords intersect inside a circle, then the product of the segments of one chord is equal to the product of the segments of the other. In the common sense language, we put it on the board, or on the in the notes, we said piece times piece of the first chord is equal to piece times piece of the second. The fancy way, the product of the segments of the first chord is equal to the product of the segments of the other. Theorem 910, when two secants are drawn to a circle from a point outside a circle, then one whole secant times its outside piece is equal to the other whole secant times its outside piece. The fancy way to say that is the product of one secant and its external segment is equal to the product of the other secant and its external segment. Now we're looking at a secant and a tangent. When a secant and a tangent are drawn to a circle from a point outside of the circle, then the square of the tangent is equal to the whole secant times its outside piece. Now, the fancy way to say whole secant times outside piece is secant times its external segment. So tangent square equal product of secant and external segment. Example. Just going to deal with the numbers here. If a secant and a tangent are drawn to a circle from a point outside, then the square of the tangent is equal to the whole secant times its outside piece. So we can solve, we get 36 equal, we're going to distribute 4x plus 16. Now we're going to start undoing. undo multiplication by division, and we get x equal 5. Number 2, I'm just going to call the tangent x. If a secant and a tangent are drawn to a circle from a point outside a circle, then the square of the tangent is equal to the whole secant, 12 plus 4 is 16, times its outside piece 4. The square of the tangent is equal to the product of the secant and its external segment. We're going to do the multiplication. We get x squared equals 64. Undo the square with the square root, and we get x equal 8. Okay? That brings us to the daily work, but let's review. When two chords intersect inside of a circle, then the product of the segments of one chord is equal to the product of the segments of the other. In other words, piece times piece of the first chord equal piece times piece of the second. When two secants are drawn to a circle from a point outside of a circle, then the product of one secant and its external segment is equal to the product of the other secant and its external segment. In other words, one whole secant times its outside piece is equal to the other whole secant times its outside piece. What about two tangents? How come we didn't put that on this list? Well, we already learned that. We called that the snow cone effect, right? Tangents to a circle from a point outside are equal. There you go. And then we have a secant and a tangent. If a secant and a tangent are drawn to a circle from a point outside of a circle, then the square of the tangent is equal to the product of the secant and its external segment. In other words, the tangent squared is equal to the whole secant times its outside piece. Okay? So there's the lesson, and we're going to go to the daily work and make some application of that. Let's just go ahead and go down here where there's some algebra to deal with. Maybe we'll take a look at number 4. Back up just a little. Yeah, we'll just take a look at number 4. What we have is two secants drawn to a circle from a point outside a circle. If two secants are drawn to a circle from a point outside a circle, then one whole secant, x plus 2, which is 2x plus 2, times its outside piece x, is equal to the other whole secant, 8 plus 3, which is 11, times its outside piece 3. So we're going to distribute here and multiply here. We're going to get 2x squared. When you multiply with like bases, you add the exponents. So you multiply the numbers and you multiply the names and you get a new name. And when you multiply with like bases, you add the exponents. That was our jingle for multiplication on page 5 of the algebra text. X times 2 is 2x is equal to 33. We've got a quadratic. We know it's a quadratic because it's got an x squared. It has an x squared and an x, so there's two different names. We need to set it equal to 0 to put it in standard form of a quadratic. So we subtract 33 from both sides. That gives us 2x squared plus 2x minus 33 equals 0. So my A is 2, my B is 2, my C is negative 33, and you're going to plug that into the quadratic formula, the opposite of B plus or minus the square root of B squared minus 4 times A times C all over 2 times A. And you're going to solve, and I'm going to leave it with you because you need that experience, okay? Number 5. We're going to get some good experience with some quadratic stuff here too. See, this is good for you. You got lots of the new stuff going on. We got a lot of old math going on. What we got on number 5 is two chords that intersect inside of a circle. If two chords intersect inside of a circle, then the product of the segments of one chord is equal to the product of the segments of the other. In other words, piece times piece of one chord equal piece times piece of the other. So 10 times x is equal to 6 times x plus 2 times a sum. You put it in parentheses and distribute. And so we would have 10x equals 6x plus 12. Remember the horseshoe of order operations, page 33? It says, do anything you can to simplify in the order. Please excuse my dear Aunt Sally looking for distributed property and combining like terms. That's the left side of the horseshoe. Bottom of the horseshoe says, get the variable that you're isolating on one side of the equal sign, remembering to change the sign when you cross over. There was nothing we could do to simplify, so that took us to the bottom of the horseshoe, which says get the variable you're isolating on one side of the equal sign, remembering to change the sign when you cross over. So now we've got 4x equal 12. We're going to undo multiplication by division, and we get x equal 3. Any questions on number 5? Okay. Got some more good ones for you to practice on there. Maybe we could look at number 7. AE, BC, and AD are chords in a circle. If two chords intersect inside of a circle, then piece times piece of one chord equal piece times piece of the other chord. So we could say 3 times AE is equal to 2 times 9. And you can finish solving that. It says the triangles are similar by. Maybe I should finish solving that so I can answer the next question. I'm getting ahead of myself here. Just a second. Let me back up. We're going to go ahead and do the multiplication. 3AE equal 18. Undo multiplication by division. And so we get AE equal 6. And so let's throw that in there. It says triangle AEB is similar to triangle what by what? Well, there's only 3 ways to prove that two triangles are similar. They're side, 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 angle, side, and angle, angle. Angle, angle is when all the angles of one equal all the angles of another. Remember that in similarity, the sides that match are not equal, they're proportional. So when you see an S in proving they're similar, you're trying to see if the sides are in proportion. What we have is that vertical angles are equal. That gives me an angle equal an angle. Now that's the only angles I've got. So I've only got one angle equal angle. To prove it by side angle side, I would need to prove that the sides that form those angles are proportional. The sides that form the angle over here are 9 and 6. The sides that form the angle over here are 2 and 3. How did we check to see if they were proportional if we weren't sure if the 2 went with the 6 or the 2 went with the 9? Well, we said we knew that small would go with small and large would go with large. So we're going to put small from the green 2, large from the green 3, over, small from the red 6, small from the large from the red 9, and reduce. 2/6 reduces to a third. 3/9 reduces to a third. An angle of one triangle is equal to an angle of another. The sides that form those angles are in proportion, meaning that the ratios are equal, so we can say that they are similar by side angle side similarity. That's chapter 7 stuff. But we also need to name the similarity with the correct stuff in order. Now, how did we do that? Well, the most obvious is that E goes with E because that was those vertical angles in there. Well, how do we get the others? Well, we had a small and a large and a small and a large. Opposite the small over here is B. Opposite the small over here is D. So B goes to D because they were both opposite the smalls. B was last, so D was last. We've got E and D, and the only thing left is C, so we have our similarity named in the right order. If they're similar, then the sides are in proportion, and so we could look at that scale of 1/3. We've got the 8 we're trying to scale down. We're going to multiply by a scale of 1/3, and so CD would be 8/3 or 2 2/3, depending on if you want it as an improper fraction or a mixed numeral. Any questions on that? Okay. All right, so we're going to leave the rest with you. We dealt with a little similar triangle thing there. All kinds of good math going on. Well, that's chapter 7. That brings us to the odd answer solutions. Don't forget to check those. And after this, we'll have the chapter study guide, which looks like the homework, which looks like the test. And we'll ease into chapter 10, which is area.